Hi, my name is Steven, and today I'm going to be talking about the predictive modeling strategy for the M4 Hackathon. The main objective was to develop a binary classification model to identify pre-diabetes and diabetes risk. So the main challenge of the dataset was the severe class imbalance. So 86% of the instances represented the majority healthy class. As we talked about in class, standard accuracy is a deceptive metric, and a naive model could achieve 86% accuracy by simply ignoring the minority class entirely. So to address this, I focused exclusively on optimizing the F1 score, which requires a strategic balance between precision and recall. Next, I moved beyond the raw data and created new features based on clinical logic. I engineered a metabolic syndrome indicator for patients presenting with high blood pressure, high cholesterol, and a BMI over 25. I also modeled the nonlinear interaction between age and BMI. By synthesizing these features, I provide the model with higher order biological signals that raw survey responses don't often show. So to accommodate this class imbalance, I implemented ADASYN, or adaptive synthetic sampling. So unlike standard SMOT, which generates synthetic data points uniformly, adaptive synthetic oversampling is adaptive and uses a weighted distribution to generate more synthetic data in areas where the minority class examples are most difficult for the model to learn. This forced the model to focus its learning capacity on the most ambiguous borderline cases. So I paired the adaptive synthetic oversampling with a cost-sensitive light GBM classifier. Gradient boosting was chosen for its ability to capture complex patterns, but I modified the learning objective by incorporating a scale POS weight parameter. This explicitly increased the penalty for false negatives, ensuring that the model prioritized catching potential diabetic cases, even if it meant a slight increase in false positives. One of the main requirements for the hackathon was maintaining strict validation integrity. So following some of our class notes, I wrapped my entire workflow inside an IMB learn pipeline. This kind of created a firewall that prevented data leakage by ensuring that synthetic data generation occurred only within the training folds. This ensured that the validation F1 score generated is a reliable predictor of the real-world performance. Finally, I utilized threshold moving to optimize the final classification. Since the default 0.5 threshold is not usually optimal for F1 scores in imbalanced medical data, I extracted the raw probability logits and conducted a search for the mathematical cutoff that maximized the harmonic mean of precision and recall. This final step was the key to maximizing the model's utility for public health. In summary, by synthesizing clinical feature engineering, adaptive oversampling, and cost-sensitive boosting with a rigorous pipeline, I was able to develop this model. Thank you.